Are segments of secants and tangents also proportional? Sure, except that the relationships, that is, the parts that you have to multiply, are different. When you have two secants, the equality in products come from the multiplication of the external part of the secant times the whole secant. The chord part of the secant, that is, the internal part, is not taken directly into consideration. Again, how can I prove that? Well, by drawing auxiliary segments that form the two similar triangles in question. These two triangles in the two secant combinations are similar. Again, we have to find equal angles. In this case, the two triangles share the same angle here. So angle 1 is equal to angle 1, and angle 2 is equal to angle 3, because they are inscribed angles intersecting the same arc. Okay, so now that we know that the triangles are similar by AA, we rotate the triangles so we could reference the corresponding sides clearly. Once the triangles are properly referenced, we set up the proportions using the corresponding sides so that 6 is to 9 and 27 is to 40.5. And cross-multiplying 6 times 40.5 is 243. And 9 times 27 is also 243. It checks. If you multiply the exterior part of the secant by the whole secant, their products are equal. Now, for the case of a secant and a tangent, because we don't have an interior part for the tangent, then the measure of the tangent has to be multiplied by itself. In other words, looking at this circle, the square of the tangent segment is equal to the product of the outside part of the secant times the whole secant. For the proof, we draw these two lines, and these are the two triangles that are similar. This is small triangle and this larger triangle. As you can see, again, there is a common angle to both triangles. So that angle 1 equals angle 1 and angle 2 equals angle 3 because they are half of the same arc they intersect. Angle 2 because it is an inscribed angle made by two chords, and angle 3 because it's a chord and a tangent. Anyway, the triangles are similar by AA. Again, we rotate the triangles to show them clearly and see that they share BC. In the smaller triangle, BC is the largest side, while in the larger triangle, it is the smaller side. We now set up the proportions AC is to BC, as BC is to CD. Notice how the common side 14 gets squared. We have the proof. The square of the tangent is equal to the product of the external portion of the secant. That's CD and the whole secant. That's BC.